Okay, so just the goal of my talk is to provide kind of a series of examples, and you can decide whether Kolmogorov complexity is essential or it's just a fancy way to say trivial things and so on. So there are two opposite views to say, simplifying the picture. Some people believe it's a powerful tool to do this or that. And other people just say that it's a way to reformulate arguments, counting arguments, or something similar, just in a more intuitive or less intuitive way. So it's just a kind of language. And actually, there are three languages, not only not two. So one, they were listed in the first paper of Kolmogorov. It's combinatorial complexity language and probability theory language. And my goal today is to give some examples of translations. So I just even found the picture, if it can be shown. Yeah. So this is maybe you have seen this picture. It's Rosetta Stone. There are three languages used in this. Of course, I cannot explain exactly what are the languages, but this is it was found in Egypt and was used to discover the meaning of the inscriptions there. One of them was Greek, and other two were, I think, Egyptian. Okay, so just as a standard introduction, so Kolmogorov complexity of a string x is a minimal length of a program which produces this string x, and if D is the interpreter of the program, D of P, we look for a minimal string P which is mapped to x with this interpreter, and of course this depends on the interpreter. And we can take an optimal one and the universal one when we first write a program and then the input. And if we take this universal one, we make the complexity minimal. It can emulate any other. And so there are several variations of the complexity, which that's one of the things which disturbs people who started to look at this field, because there are too many notions and even more notation for this. So there is a picture. Actually, there are four main varieties of versions of complexity, and actually they are. It's not just randomly chosen for definitions. They have some reason why they appear. So both the string P, which is a program, and the string x, which is data, can be understood in different ways. So we can believe that the object is finite, is given from the beginning to the end, and just a string, for example. And another view, which takes into account the structure on the object. So we want to to consider each string as a description of as a prefix of an infinite sequence. So, for example, we can try to find. We can say that a program is given on a tape, and we should read the tape and stop when we want to stop. And what we have read to this moment is the input. So, but that's a technical classification, and in most of the examples which we'll try to explain, then it's not really used. But still there are several. So there is most common the initial Kolmogorov version, which is because of that called plain complexity, and it was in Kolmogorov paper it was denoted by K, and now it's usually denoted by C. And there is other prefix complexity which was introduced by Levin and then rediscovered by Chaitin, and Levin denoted KP, but then now it's more K of x is more useful. And also there are some other complexity, decision complexity, monotone complexity, and to make picture even more complicated, there are also conditional complexity, which is a minimal x conditional complexity of x given y. So we ask for a program which transforms an input y to output x. And we look for a minimal length of this program, its conditional complexity. And actually, now there are 3 objects, P, X, and Y, and each of these 3 objects can be considered in 2 ways. So we get 8 versions of conditional complexity. Fortunately, most of them are, it's rarely important which one we use, but sometimes it is. And also, there is one other thing which I will not really use today, but just I want to list it here. It's a priori probability. It's when we measure not the complexity of describing an object, but we measure the probability that this object will appear randomly. And actually, it's very close to complexity, and so this is main technical notions. Okay. So let's switch to our first. So what I will say will be just a sequence of examples. I don't know whether we'll have time to cover all of them, but they are completely independent, or almost completely independent. So first example is the philosophical one, which was the motivation of the entire theory, I think, for Kolmogorov. So there is a philosophical problem which goes back to I think 18th century or something like this. So what is randomness? So what is it's a property of an object, or it's a property of a process of generating this object. So for example, imagine that in the shop we can buy something which is advertised as a well-shuffled deck of cards. So you can open it and start playing without preparation. So you can buy. There is a box with these things, and the question is, if we want to have kind of quality control, how it should be performed. So imagine we open such a deck and see the cards 1, 2, 3, 4, and so on. So it seems to be not well shuffled, but on the other hand, all the ordering have the same probability if it's really well shuffled. So it's not clear whether this notion has any meaning. And not only philosophers speak about this a lot, but there is even cartoons. If you look at Google, just for words random and cartoon and or fair dice or something like this, I just found this funny thing, which says that it's just the same problem whether a number is random because it was chosen in a special way, or it should be a property of the number. And one of the possible answers to this question is provided by Kolmogorov complexity, which says that we can define randomness as a property of an object, not the process. We can just say that this string is more random, or almost random, and this string is not random. And this is just the idea is to identify randomness with incompressibility. So it's just inability to find a shorter description of the string than just to list all its elements. So and you can do it for infinite sequences, and there was technically another definition of Martin Löf, which based on constructive measure theory, but it's equivalent to there is a Schnorr-Levin theorem. A sequence of infinite sequences can be called random if and only if complexity of its n-bit prefix here is at least n. So here we technically we need to use monotone or prefix complexity. You can use also some. There is also some criterion with plane complexity, but generally the philosophical idea that randomness of a sequence is incompressibility of its initial segments. And then we can translate classical statements of probability theory to Kolmogorov complexity language. So for example, this is also classical example. So there is a strong law of large numbers which says that a randomly chosen sequence according to uniform Bernoulli distribution, just fair coin distribution, always have the limit frequency 1/2. So it's called strong law of large numbers. The frequency of you have as many tails as heads in a long prefix, almost as many. And now we can split it into 2 statements. First, we say that every, without any, not almost every, just every algorithmically random sequence has this frequency 1/2. And then another statement is general, not related to the specific law. It says that this Martin-Löf, or well, in this definition, it's called Martin-Löf sequence because the first author of these definitions, they have almost every sequence is a Martin-Löf random sequence. So then we have, so in this way we split a specific law of probability theory into two things. First is specific one, which depends on the law we are interested in, and second is just a general statement about Martin-Löf definition of randomness. So this is one example of from classical probability theory, and another example, I should say, it's a kind of philosopher's view on what you have heard yesterday. So imagine there is a device that has a button. You can push this button, and the device becomes switched on, and produces some n-bit strings and stops. So just you can buy such a box, and it's advertised as a device producing random strings. So how can we understand this advertisement? And this can be done again in two different ways. First, you say that the classical understanding, the output distribution of this device is close to the uniform one. And the second effective understanding is that with almost in all the cases, the output string is incompressible. So it's different and seemingly unrelated things, because first say something about the distribution, and the second one also speaks about distribution, but it just says that the distribution is concentrated on some specific set of incompressible strings. And of course, if there are no assumption about the device, maybe there is just one incompressible string inside compiled in, and then it always produces the string. So without additional assumptions, device can satisfy the second one, but not satisfy the first one. And in the other direction, the first one implies the second one always. But if the device is simple and algorithmic, then one can say that these two properties are related. Now, of course, as usually with philosophers, here we ignore the most interesting technical part because of choosing a long string and making a random choice, a random element of the string, and all the technical things about this Kullback-Leibler divergence and so on. So this looks almost trivial, but this doesn't, as with philosophers usually. But it doesn't mean that underlying theorem is so simple. But I still believe that this is some kind of very high-level description of what is happening. So the classical discussion about probability in algorithmic and classical settings is now transferred somehow to finite things, and in a very nice way. Okay, so this is my second example, and now I want to show you why Kolmogorov complexity is indeed just a language to use to reformulate standard arguments. So I will give now I have chosen a very simple, probably the most simple I can find, example of an argument when we use Kolmogorov complexity for existence proof. And so first, the problem is we want to find there is a matrix without uniform minors. So we look for a big matrix, n times n, and minor is obtained by choosing k columns and k rows. So we have k square elements, which are I tried to simulate this cartoon style, but not very successful. So we take the minors on elements on the intersection of these columns and rows. So we have k square minor elements, and we have n square minus k square elements outside the minor. And the minor is uniform if it's just 0 or 1. All elements are 0, all elements are 1. And there is a claim. So we can find an n times n bit matrix which doesn't have k-type case uniform minors. Of course, for small case, it's not possible. If k is equal to 1, then every matrix has a uniform minor, all the minors are uniform. And if you look for a 2 times 2 minor, it's also easy to prove that big enough matrix always contains it. And actually there is a logarithmic bound. So it's 3 log n is not very far from the best possible thing. So, but the claim is that if we want a reasonably big minor, 3 log n, then we can find a matrix without such a minor. Okay, so how the people normally explain this thing. So let's start with a counting argument. So we just want to count matrices which have a minor and show that that's not enough to cover all the matrices. So how many matrices have a uniform minor? So first we should count how many positions for this minor exists. So each row can be chosen in n ways, and if we ignore some dependent relations, we can say that there is at most n to the k ways of select the rows. With k times we should select one of n rows, and the same number for columns. So there is at most n to the power 2k positions for the minor. Now we keep in mind that k is log n, but just there are 2 types of minors. It can be 0 minor or 1 minor. And if we know which are the positions of the minor, what position the minor occupies and what type it is, then we should also, after that, we should count the different possibilities for the rest. And there are n square minus k square places when we should choose 0 and 1. So we have that many combinations. So now we have to multiply the things, and if we do it carefully, so we n is 2 to the log n. So here we have 2 to the log n. Then we have this 2 which is here, and then this k which is 3 log n, and this times 2 gives 1 here, and here is n square minus 9 log square n. But anyway, here is 6 log square, and there is 9 log square, so we get something less than total number of matrices. And so in this way we show that there is not enough matrices with uniform minors to cover all the matrices, so there is one without. So this is the simple counting argument, and it's equally simple when transformed to Kolmogorov complexity language, which can be, I just give the parallel description of it. So first, let's show that in every matrix which has a uniform minor is compressible. So we can describe it shorter than just listing all the bits. So how do we describe a matrix with uniform minor? So first we say we need log n bits to specify each column or each row. So we have 2k log n bits in total. So, and of course you see that it's exactly corresponds to this thing. And then we need one additional bit to specify which minor it is, 0 or 1 minor. And then we need n square minus k square bits to specify the rest. And we made the same computation, the only difference that it's done in after taking logarithms. So we get 2k log n bits to describe the position, 1 bit to describe the type, and n square minus k square to describe the rest of things. And we get again the same computation and say that it's less than n square. And so we are now lucky because we can explain it a very scientific way using a notion of Kolmogorov complexity and so on. But actually it's not we have to pay for this because in Kolmogorov complexity is defined only up to a constant. So strictly speaking, this is not a good argument. We should either deal with some asymptotic way or so if you look at Lee and Vitani book, when it's there are many examples of this type, and always this problem of constant, asymptotic constant is somehow hidden somewhere. But let me give also a very simple but less trivial example of translation. Still it's almost a translation, but so there is a classical result about palindromes, and we can use a different form. We say that copying an n-bit string requires n squared time. So we have one tape Turing machine. So I tried to make an illustration. So this is a tape, and this strange thing is a head, and we have a string x, and our goal is to copy the string x and have the string x here also. And it requires a quadratic time, n squared time, and so how can we explain it using Kolmogorov complexity? So the statement in complexity language is the following one. So first of all, we can assume that the second half of x is empty. So we have a kind of information here, and then we need to bring this information here. So this is a question of how fast the information can be transferred by a Turing machine with one head. And indeed, there is a simple, very natural bound that if initially tape was empty, so imagine we have some kind of border, and initially tape was empty, was completely empty here. And we are looking on the complexity of this zone. So this is a kind of border zone, as you, those of us who lived in Soviet times knew that near Soviet border there was a big zone which was almost empty. You cannot go there. So imagine we have this border zone, and it's we are interested only in the complexity of the part of the tape on the right of this, outside this border zone, and we look on the complexity after t steps of the computation. And the complexity is bounded by n over, no, it should be not n, by t, sorry. T steps of computation, excuse me. So indeed, to bring one bit of information through to carry this one bit of information across this border zone, you need d steps. So and the capacity of your head is limited, so you can bring only finitely many bits of information in each round. So you need t over d. At most, in t steps, you can bring almost t over d elements. So this is informal description. If you look for a formal description, it's just the classical trace methods, but now it can be explained in an easy way. Imagine there is a kind of we install some kind of border guard somewhere in this border zone, and this border guard, when a messenger at head of a Turing machine is crossing the border from left to right, it always writes down what is in the head of the Turing machine. So we have kind of record for any position. We have a record what were the contents of the machine when it went to this zone. And if we know this information, we can reconstruct the behavior of the machine on the right. So actually, independently of the place when we place the border guard, we can the record is enough to reconstruct all things on the right of the inside this zone. And so the length of the record should be small, not very small, at least the complexity of this right-hand side. And so then we can say that the sum of the length of the record is just the time of computation. So we cannot bring much things. So it's just a standard argument, but explained, as I believe, in a more intuitive way. So in the previous one example, there was no advantage. They are just translation. And here it becomes a more intuitive somehow. But let's go to other examples. For example, there is a story of everywhere complex sequences. So it starts with complexity side. So we know by definition that a random sequence has complex, incompressible prefix. Prefix of a random sequence has complexity n up to a constant. But of course, it's only for prefixes, because a random sequence should contain all the possible combinations of bits. So some factors should be just 0 or all zeros or all ones. Every string should be somewhere in the sequence. So we can ask for a super random strings. So they are more than random, so they are not random actually. And they should be called everywhere complex. So we want that every substring has complexity we cannot have this n, but just let's take 99% of n minus some constant. So we look for one infinite sequence where every substring has complexity close to n. And indeed, it's possible. And it was shown by Levin used Kolmogorov complexity. And also what is interesting is it has some direct combinatorial translation. And combinatorial translation is, so imagine we have some set of strings, forbidden strings, f. And if we look at strings of length n, then it's not all strings are forbidden, and at most that many strings are forbidden. So it's just, you see, there is just a number of strings, and here is the complexity bound, and they are corresponding to each other. And then there is a sequence such that all sufficiently long substrings of this sequence are not forbidden. So you can prove, even if you don't know whether this is true or this is true, you can prove that they are equivalent. These two statements, one combinatorial and one complexity, are exactly equivalent. And then, of course, you can go in both directions. You can use combinatorial proof, which you can obtain by Lova's lemma, and there are interesting other combinatorial argument by Rumyantsev, Miller, and Muchnik. There are different flavors. And you can go also in other direction. You can start with complexity proof, as Levin did, and then you can translate to consider as a proof of combinatorial thing. And they are not so easy to have a direct translation from one to other. Okay, so this is next example. And also there is example from coding theory. So what is coding theory about? We have the simplest version. We look for an n-bit strings, and we want them to be far in terms of Hamming distance. So the main question of coding theory, in a sense, is that we have n, we have two numbers, we have n and we have d, and we want to pack as many strings as possible in Boolean cube of dimension n, and the requirement that every two of them should be at least d bits apart. So the reason for this is then we want to decode, then we can decode even if they are less than. So there is a lower bound for this. One of the first statement of coding theory is a lower bound for this, which is called Gilbert-Warshamov bound. And the idea is that if we have such a thing, why we want this big distance? If we have such a coding code words, then if our enemy changed in transmission, some half of the d bits are changed, then we can still have no confusion with the other thing. So we still are in the small ball around the point, and this ball doesn't intersect with other ball. So we can decode it safely. Of course, there are much more complicated things, how to decode things efficiently, but even the question how many of them can be found is still, there are lower bounds and upper bounds, and there are no exact answer. But there are other, imagine if we have a transmission line which can not only corrupt one bit, but also just miss some bit or add some bad bit, then of course this bound which we had before about the distances is not useful anymore, because it doesn't guarantee the possibility of reconstruct things. So we can look, if we want to look, we can look specially for the codes which are stable to insertion or deletions in transmission. But we can just look on general requirement. Imagine what we want, that one code word cannot be obtained by a simple transformation of other one. So we cannot get a code word xi by just applying a short program, a program of size less than d, to some other code word xj. So for example, deleting one bit is a relatively short, simple program. It's just log n bits in this program. So deletion and changing a bit are all special cases of this general requirement, that the strings should be somehow independent, not easily obtained one from another. And now we can ask ourselves whether how many strings we can find with this width property. And the answer is actually even easier than technically looks like more natural for this. It's just we can find 2 to the n minus d strings which are d-separated in this sense. And if you consider special, if you try to get Gilbert-Warshamov bound from this, you get exactly the same expression up to constant. So you can really think as a trivial generalization of Gilbert-Warshamov bound and for other types of distortion during the transmission. Also, there is a kind of explanation what is the connection between complexity and combinatorial statements. So I'll give a very simple example. So there is a statement which says that complexity of a pair is at most sum of complexity of the first term and conditional complexity of the second term. It's trivial. We should first describe our first term, and then it's enough to add the program which transforms the first term to the second one, and then we can reconstruct the pair from 2 things. And there is a logarithmic term of log means log of the length of x and y. So this is a technical thing, but then we can explain what is the combinatorial translation of this. So imagine we have some set of pairs. No, I draw it on a real plane, but actually it's discrete. Here are strings and here are strings. So we have some set of pairs, and there are 2 parameters of this. One, which we can call width, is just the number of elements in the first projection of our A, how many first components appear. And another is, which we call height, is just the maximal number of the second components with a given first one. And of course there is a trivial bound. A is bounded by the product of the width and height. It's trivial. But also it's equally, our original complexity bound was also trivial. What is not so trivial for complexity is, it's probably the first non-trivial result about complexity. It's very easy indeed, but still it requires some argument. It's Kolmogorov-Levin theorem. It's an inequality in another direction. So if we have a complexity of a pair is small, then either the sum, this should be small, either so the way to describe pairs as we have seen in this inequality is in fact the optimal one. And again, it's with the same precision, logarithmic precision. And then we can just formally rewrite this inequality in a more convenient form. If complexity of the pair is less than sum of 2 numbers k and l, whatever this k and l are, then either the first term is smaller than k plus this O of log, or the second term is smaller than l. So this is just a formal equivalent of this inequality in a bit strange way. But now it's from this we can see what is the combinatorial version. That every set of size 2 to the k plus l. So this is here. So every set A of pairs which has this size can be split into 2 parts. One part has a small width. The width of the first part is 2 to the k, and the other part has small height. So the height of the second part is less than 2 to the l. And also it's a simple combinatorial statement, but I think that this is the correct translation of this inequality in the combinatorial language. And there is other, probably you have heard from me, some of you have heard from me this example, but there is an equality of complexities or Shannon entropies actually about this for 3 strings. This is a complexity of triple is bounded by the sum of complexity of pairs. And it has a very nice, if you can understand what is here. So this is a 3-dimensional, some 3-dimensional thing, and we project it into 3 different planes, vertical, horizontal, and other vertical. And the volume of the entire three-dimensional body is bounded by the product of three areas. Projection of on two horizontal plane and two vertical projections. It was, I think it was one of the problems for some Olympiad, and then there's some general version of this thing was called Shearer's lemma, and then here we see that how it can be proven. Actually, it can be made a proof using Kolmogorov complexity. And also there is this proof in language of Shannon entropy is possible. So it's kind of, it was found for Shannon entropy also without knowing about Kolmogorov complexity. And also there is another combinatorial and information theory question which I want to show. So there, imagine we have two strings, A and B. So there is a notion of mutual information. So we can measure the complexity A and complexity B and add them. So if A and B are somehow independent, then the pair should have the same complexity as the sum of the complexities, because there is somehow no common information. And in general, we have some string A of some complexity, string B of some complexity beta, and the complexity of the pair is in general smaller than the sum of complexities, some gamma, which is smaller than alpha plus beta. Because there is some, informally it's just a symbolic picture, there is some intersection of information in A and B. And this intersection, we can measure the amount of information here just by taking the difference alpha plus beta minus gamma. So this is the economy because of alpha and beta are described not independently but together. And this is just a quantity which we can define for every two strings. But now we can ask whether it's really can be understood in information theory. So imagine there are two people, A and B, which want to know, they want to know strings A and B. And we want to send some messages. And there is one message which we can send to both of them. And then there are messages which we want to send separately. So the question, maybe we can just have messages of these three lengths, which is alpha minus delta. Delta is the differences. So alpha minus delta, delta and beta minus delta. So there is a kind of common information of size delta, and separate information of this size and this size, and maybe this all will be enough to reconstruct A and B. So sometimes it's possible, but sometimes it's not possible, and this was found first by Gach and Kerner by some probabilistic construction, and then this question was investigated by Andrei Muchnik also, and there is a combinatorial equivalent of this question. And the combinatorial equivalent is that we want to cover a graph with minors. So what is it? Imagine that we have a graph, left part has 2 to the alpha elements, right part has 2 to the beta elements, and the graph is almost uniform. So there is a degree of each vertex is about 2 to the delta, and the graph has 2 to the gamma edges. So we have alpha plus beta minus gamma is delta. So this is what corresponds to the pair AB. And what corresponds to this picture when this transmission information is possible is just the possibility of cover the graph by 2 to the delta minors. So a minor is we select some set of this size on the left, select some set of this size on the right, and connect the sets with all edges, all possible edges. So we have a minor which in terms of matrices, we have just a minor all full with ones. And we want to cover our initial graph by these minors. And the possibility to extract information is somehow equivalent to the possibility to cover the graph by the minors. And there are some quite non-trivial things about this. So, for example, recently Ilyar Eisenstein, who gets some bound for some specific graph, how many minors we need, And it shows that in algorithmic terms how big should be this delta to transmit information as we want. Okay, so let's move. There is another combinatorial example. So imagine we have a set of pairs. So let first me explain the definition. So here is this set of pairs, and this set is not uniform in the following sense. The most vertical sections are very small. So the average vertical section is also small. But some of the sections are very large. So the non-uniform means that maximal section is much bigger than the average section. And this you can measure this by a number which is called non-uniformity. And so there is a theorem, simple one, which says that every set of pairs can be represented as a union of not very many sets, and these sets are almost uniform. So both the number of sets and the non-uniformity actually in both directions, we require in both directions, vertical and horizontal direction. Both of these parameters are polylog of n, and really what we want is a multidimensional version of this, but it's similar. And what is interesting about this theorem, that you can almost for free get a proof of this theorem using Kolmogorov complexity. And when we want to cover these parts which we want to use for covering are just the strings, the sequences of tuples of strings which have some complexity, satisfy some complexity bound. So the complexity of different things is bounded by different constants. So these are the parts. And it's easy to see that they are all the parts are almost uniform, and there are not many of them. So Kolmogorov complexity proof is so simple that it's not clear how we can translate it combinatorial, because there is almost nothing to translate. But you can find a combinatorial argument, and you can even prove a stronger thing with a combinatorial argument. But this combinatorial argument looks completely different. It's not a translation of a complexity one. So this is our next example. Also, there is Shannon coding theorem, in basic first theorem in information theory. So we have a random variable, and each has k values, and they have some probabilities p1, pk. And then we consider n independent trials of this variable. And the question posed by Shannon, how many bits we need to encode the typical sequences of this n trials? And the answer is that we need, Shannon's answer was that we need n times entropy of this variable. And entropy is defined like this. So this is a frequency, a probability of each outcome, and then it's multiplied by the kind of surprise value, surprise measure when this outcome happens. And there is a formal statement of Shannon theory. It's well known and a bit complicated, but what I want to show here, say here, is that it's very simple translate to complexity version. So we just say that with high probability, the string, which is the value of this random variable, has Kolmogorov complexity close to this nh of psi. So it seems that in this way, it's much easier to formulate the Shannon coding theorem easily. And there is even a funny connection with other things, with combinatorial things. For example, looks again on the same inequality. So we have this inequality for complexities, we have this inequality for entropies, and moreover, we can get almost, it's equivalent in a sense. We get inequality for the size of groups. So imagine we have a group G and 3 subgroups of its. So instead of 3 variables, we have 3 subgroups of some group. And then we can look on the cardinalities of this intersection of all 3 groups and intersection of pairs. Well, actually, log G can be cancelled somehow in 2 of them things. So, but in this form, it's easier to understand the relation with our complexity inequality. So if you don't just to want to see, to convince somebody that Kolmogorov complexity theory and information theory are useful, you can just try to suggest to prove the statement, just not knowing where it came from. And I think it's not so trivial. So I think even group theory experts, it's not so easy for them to prove them, because the intuition of the proof is more information theoretic. But still, it's true. And actually, the general statement that for Kolmogorov complexity, for Shannon entropy, and for group sizes, the inequalities are the same. So Andrei Ramashchenko have shown that for Kolmogorov complexity and Shannon entropy, the linear inequality are exactly the same. And also later, two people from Hong Kong proved that the same inequalities, without actually, they didn't know about Kolmogorov complexity much, they just worked with Shannon entropy. They proved that the same inequalities are for groups. And there is also a very strange inequality. I think it was discovered by Kosti and Yura Makarychev, Andrei Ramashchenko, and Kolya Vereshchagin. This was published in this paper, I don't know. And I just wrote it, I hope it's correctly written, but just the idea is to show that there are quite non-trivial inequalities. And it's also related with a nice theorem of Andrei Ramashchenko about extraction of common information. But let me just show this strange inequality. And also there is another theorem, it's Andrei Muchnik theorem about conditional description, which I think is one of the most novel results in Kolmogorov complexity, in general Kolmogorov complexity in last decade, which we already have discussed this yesterday. So if we have two strings and we look at a program, conditional complexity, we look at a program of P that maps A to B. So by definition, this is the minimal possible length of such a program. But also, if we want this additional restriction, this program we want it to be simple relative to B. So the program should be somehow inferable from B, and then of course we can find such a program. Just map everything to B is simple relative to B. We don't know any other information. But it's not minimal. And the theorem of Muchnik was that you can combine these two conditions. You can always find a program P which is maximally simple in itself and has zero complexity relative to B. And what is interesting that there is information theory analog, Wolff-Slipan theorem, and they seem to be quite independent. Also, there are some similar technique was developed for not only by Muchnik but for different purposes by Fortneau and Lapland, and they used a randomness extractor instead of expanders like Muchnik. And then yesterday we heard this, how to use explicit extractors and how to use a de-randomization to get space-bounded versions of this. Okay, and then let me I'm running out of time, so let me just show simple examples from general computability theory. There is Post theorem. Post theorem said that there are simple sets. Simple set is a numerable set when we cannot generate elements from the complement. And there is a construction using Kolmogorov complexity. It's funny that it's also used the word simple in quite different meaning. So we say that a string is simple if complexity if it's highly compressible, at least twice. And most strings are not simple, so the set of simple strings has infinite complement. But we cannot generate effectively non-simple strings, because if we can, then we can generate long of them, arbitrarily long non-simple strings. So we can generate strings with arbitrary high complexity. And in this way, we can assume that we can compute for given I, compute some string of complexity at least I over 2. But then, on the other hand, we need to specify, if we have an algorithm, then to specify the string, we need to specify only O of log I bits. And so this is less than I over 2. And so we come to Berry paradox, which you all know, and get the contradiction. And also there is an example about Lauer semi-computable random reals. So it goes back to constructive mathematics. So if we have a computable converging series with positive rational terms, the sum is not always computable. And there is, let me just show the entire picture. So there is some kind of classification. Not all of these non-computable numbers are the same. So some of them are more non-computable and others are less non-computable. There is some classification due to Solovay. And they are maximal element of this classification, and they are random reals, reals whose bit representation is a random sequence, and you can even find a classification in terms of busy beaver functions. But okay, we have no time to go in this. I just want to show shortly remaining examples, and they can be found in the proceedings, which happily are now here. So there is a Lover's local lemma, which says that if you have a CNF and it has the property that the clauses are not very dependent. So each clause has k literals, but each clause has only O of 2 to the k neighbors. And neighbors are the clauses which share some literal. And such a formula is always satisfiable, and there is a non-constructive proof given by Lover's local lemma. But recently there was a kind of breakthrough, and it was a best paper of Stock, I think 2009, that you can just use a naive algorithm. A naive algorithm is just take any valuation of the variables, and if some clause is false, you should replace it with all the variables with new fresh random values. And if you do it along enough, and you don't need to do it long, it terminates quite quickly, and you get the satisfying assignment. And the explanation, there is a simple explanation using Kolmogorov complexity, and if in one sentence compressed, it's here. So if this algorithm not terminates for a long time, then the sequence of resampled clause somehow encodes the random bits, which is impossible. Okay, there is also another example, which is Chaitin popularized this a lot. So how the Gödel theorem in Chaitin form. So we look the statements of the form that complexity of some string is bigger than something, and then we cannot prove all of this statement, because otherwise we get better paradox again. And what is funny that recently there was the same approach to second Gödel theorem. There is a small note of Krichman and Truss, which use this unexpected test paradox about the test which will be given next week at some day, but you will never know before this day whether the test will happen or not. And it can somehow it's related to the second Gödel theorem. You can find a proof of the second Gödel theorem. Also, there is a 13th Gilbert problem, whether any function of more than 3 variables can be represented as a compositional function of 2 variables, and there were some results for continuous case, and there is an very interesting unsolved question for finite case. But there is a Kolmogorov complexity version. Imagine we have 3 strings on a blackboard, and there is a game. We are allowed to add a new string if the string is simple relative to 2 of the strings on the board. So new string can be dependent only on the 2 strings already there. And the question is what we can obtain in finitely many steps. Of course, we can get only strings which are simple relative to initial strings, but strangely not all of them. And this is a version of Hilbert's problem for Kolmogorov complexity. Okay, there are also some things about secret sharing, which we heard a bit before, and some kind of quasi-cryptography statement about a result proven by Muchnik also. So let me just finish here, not going into detail. And I want to show you the picture of Andrei Muchnik, who was actually, Kolya said something about Kolmogorov seminar, but I should say that if there were technical organizers, but if you want to say something about the leader of the seminar, it's definitely the most deep ideas, and almost all our work was inspired by Andrei Muchnik, our friend who died several years ago. And here there are two pictures. This is one of the I think it was taken in CSR here. And this second picture is when he was a student of Moscow State University. And this is, so I'm grateful to Organizator to the possibility to present some works inspired by Andrei and done at our seminar. So thanks. Yeah. So there is a funny question. It was posed many years ago, and even I gave in St. Petersburg. There was a conference in Euler's Institute. I remember that I was giving a talk about this. So we can add to our. There is a kind of random mathematics. So we can toss a coin, get a sequence of 1,000 bits, and say that the sequence is compressible. And this is an axiom. Maybe and most probably this is true. And then we can use this axiom to prove some interesting. Maybe interesting theorem about something. But actually, recently it was asked by, I think by Lipton or somebody else in the blog. So I found that it's not on, it's indeed a natural question. But the answer is no. So if you want to prove some interesting theorem using this random process, you get the same, or you want to prove any specific theorem using this random process, your chances to do so are exactly the same if you're trying to prove some false theorem. So it doesn't help.